Right. So, okay, brilliant. Thank you very much, everyone. So my name's Dr. Aidan Rhodes. I am the Research Fellow for Energy Policy Briefing Papers at the Energy Futures Lab here at Imperial, and I'd like to welcome you to our launch of our new white paper, which is on the future of nuclear power in the UK, challenges and opportunities. And for those of you joining us for the first time, especially online, the Energy Futures Lab is one of 7 global challenge institutes here at Imperial College. We were founded in 2005 to address basically the world's major energy challenges by bringing together teams for a variety of research backgrounds to produce interdisciplinary energy research. So, as many of you are aware, nuclear power is low carbon source of energy production, second largest source of low carbon electricity globally after hydropower. The UK currently generates about 15% of its electricity from nuclear power, about 6.5 gigawatts. However, much of this is scheduled to be shut down over the next 10 years. So if the government's goal of 25% of electricity production to come from nuclear is to be met, there is a strong need to investigate both current and future nuclear power technologies and work out costs, policy and funding mechanisms. So this paper looks at that and evaluates the prospects for new nuclear power generation. So in a moment, our lead author, Nadeem Mustafa, will take us through the key messages of the paper, and this will then be followed from remarks from our invited panelists, who you will meet in a few minutes. We'll then move to a Q&A session with the presenters and the panelists. So there'll be an opportunity to ask questions. Please absolutely do raise your hand, or if you're online, please put a message in the chat box, and we will pass that to our panelists to answer. Finally, this is being recorded, will be available on our YouTube channel. We'd encourage you to share the recording around with colleagues who weren't able to make it. And the white paper itself is available from our website and will be circulated. You'll be sent an email with a link to the paper after the event. And now to introduce the paper and give the presentation, I'll hand you over to Nadeem.
Yes, okay. Hi everyone, I'm Nadine, and as Aidan mentioned, I'm the lead author of this paper alongside Megan Owen and Aidan Rhodes. And today I'm going to speak to you about the future of nuclear power in the UK, challenges and its opportunities, and kind of what we have in the paper so far. I'm not sure where it stands, so you can see. Okay. So just as an overview of nuclear power, I assume a lot of people here already know this, but essentially nuclear power generates electricity using heat produced from nuclear fission, mostly as of right now, and it's a low carbon energy source. The reason this nuclear power is quite popular, or people are kind of talking about it, is because it's a low carbon energy source. It has a high energy density, so that means that a small amount of fuel can actually produce a large amount of energy, and it's a reliable baseload power, so it can operate continuously, unlike, for example, renewable energy. Some of the challenges, though, are the fact that it has a high initial capital cost, a long construction time, which usually takes a bit over a decade or around a decade, and then looking into how are we going to handle the waste, especially that it includes radioactive waste. And so if we look at it from a technical perspective, there's quite a few generations of nuclear reactors that started all the way from the 1950s to what we anticipate to have in the 2030s. And as you go from generation 1 all the way to generation 4, essentially you increase the efficiency and the way the safety is done, as well as when it comes to generation 4, you're looking at minimizing waste and looking at sustainability as part of it. But essentially, generation 1 was the first one, and then generation 2 had an improved safety and efficiency, kind of the backbone of the current nuclear power fleets. Looking at generation 3, it had enhanced safety features and better fuel efficiency. And then generation 3 plus, you started looking into minimal human intervention when it comes to the safety systems. And then finally, generation 4 is where, as I mentioned, we're focusing more on sustainability, minimal waste, and a higher fuel efficiency and improved safety. And so how does this look like globally? Essentially, you can see here a map on the left. The darker the color, the more nuclear power is produced in the specific country. So you can instantly see, some of the top 4 are the US, China, France, and Russia. And I just kind of wanted to highlight what's their role in the global power production of nuclear, the global nuclear power production. And so the US is the largest producer of nuclear power, and you can see that here through this bar chart in terawatt hours, with the 93 operational reactors, and it approximately produces 30% of the world's nuclear electricity. Whereas in France, although it has less nuclear power production compared to the US, but it's around 70% of France's electricity is actually produced using nuclear power. China aims to significantly increase its nuclear power capacity, mainly to reduce its reliance on coal due to air quality factors and climate change initiatives. Whereas Russia is also a major player and a major exporter, actually, of nuclear technologies in Europe, Middle East, also where I come from, in Egypt. So these are kind of the major players in nuclear power globally. And then if we want to focus a bit more into the UK and what's happening within the UK, so you can see here on the right, there's a map that shows you all the different sites and reactor sites in the UK. Some are planned, so specifically Sizewell and Hinkley Point, and some are active and some are decommissioned. And as Aidan mentioned, actually quite a few of those some of those have been decommissioned over the past couple of years, and quite a few of those will also be decommissioned in the upcoming couple of years. And so just as a recap, and Aidan already mentioned quite a bit of this, but the UK generates approximately 15% of its electricity from nuclear power using those 15 operational reactors, and they kind of combine to 6.5 gigawatts. But most reactors are aging, as I mentioned, and so a lot of them are scheduled for decommissioning. The newest reactor, Hinkley Point C, is under construction, expected to provide 3.2 gigawatts of capacity. And the UK government actually has quite ambitious objectives and ambitions and plans, right? So it's aiming to generate 25% of electricity from nuclear power by 2050. Note that obviously the energy demand kind of increases from now till then. Sizewell C, as I mentioned, is another proposed project in a similar scale to Hinkley Point C. And also the UK is actually investing in innovative reactors such as SMRs, specifically the ones that are coming out of Rolls-Royce. And so just kind of to show you what's been in the report, you can feel free to read the whole report, but essentially, I'm not going to go through everything in this presentation, but I just wanted to also highlight what is in the report. So there's sections about what's happening globally, the technology, there's quite a bit on that there, so all the different reactors, how do they produce those nuclear power, what are the kind of differences between them, all the way from generation 1 to 4, as well as what's happening with small modular reactors. And then there are sections about the safety and decommissioning and waste management. There's also a section about what's happening in the UK and what we anticipate to happen in the UK. And then there are sections about economic analysis, which I'll focus on a bit more in this presentation. What kind of skills and workforce requirements would we need? And international collaborations to kind of reach the nuclear power goal that we want to globally, and obviously help within our net zero strategies. And last but not least, some research and policy recommendations based on the work that we've done in the previous sections. And so just to show you here, so this economic analysis followed the IAEA methodology. One of the main things that we've done is basically look at different scenarios. Obviously, any sort of economic analysis comes with assumptions and hence uncertainty. And so looking at it from a scenario perspective is quite helpful. And the things that we've changed, for instance, are the discount rate, so varying from 3 to 5 to 10, the capacity factor of the nuclear plant, 85 to 92, for instance, a scenario looking at a longer construction period, so 5 years versus 10 years, and then also looking at extension of nuclear plants, because that's something that you can do. You can extend the lifetime of a nuclear power plant. So for instance, even if it's scheduled for 60 years, you can extend it, and it could be, for example, operating for 80 years. And based on those different scenarios, you can see here this bar chart shows you the cost, the levelized cost of electricity for the different scenarios, specifically for the EDF pressurized water reactor. And essentially you could see that, as I mentioned quite early on in the presentation, capital cost is one of the major cost contributors when it comes to nuclear plants. It accounts for around 52%, depending on which scenario you look at, but around 52%. But then you have other things like the fixed O&M, the spent fuel management, like decommissioning, which actually shows you that when you do the economic analysis, you have to consider decommissioning costs, and hence kind of backing the safety aspect of nuclear power plants. One of the things that is heavily noted is the fact that high discount rates significantly increase the project costs. So for example, it can actually increase the cost by 90% if the discount rate changes from 3 to 10%. This is quite crucial when it comes to nuclear power plants, as opposed to, for example, CCGT, so combined cycle gas turbines, or renewable power, because of this high initial capital cost. And so the discount rate actually makes a huge difference when you look at the LCOE. And a disadvantage of this actually is that if you purely just look at LCOE, it does not fully account for advantages of the nuclear power plant, such as the longer operational time, but also the fact that, for instance, it's a baseload power generation. So it's not dependent on flexible things such as solar and wind. So that kind of takes out the advantage of nuclear power when you're looking at purely LCOE, if you're comparing it to other power generations. But in hindsight, it's still a good measure to kind of look at it, especially from a scenario analysis perspective. I'm not going to take too long on this slide. There's a lot more on this in the paper. But essentially, you could see here, those are the different scenarios that were mentioned, and then the levelized cost of electricity in pounds per megawatt hour, and then the different reactors that we looked into. So we looked at EDF, we looked at EPR, and then the European designed AP1000 pressurized water reactor, the CANDU reactor, the Rolls-Royce SMR, and then the ABWR. Those reactors were chosen based on what's proposed in the UK, and so this is why we've done the analysis based on that. And I'm not going to go through all the different numbers that come up, but I just wanted to kind of highlight that economic considerations under different scenarios actually highlight this balance between upfront investment and long-term operational costs. And so it kind of shows you insights into financial dynamics, and you kind of need to look into the different scenarios and what would happen, for instance, if you plan to construct this nuclear power plant in 5 years, but it ends up going into 10 years. And it kind of showcases, in this case, that you really need to mitigate any kind of delays when you're, for instance, when it comes to construction period. And that's how some of the recommendations come along, using those kind of numbers. And so we did this little exercise by looking at, so this graph here shows you the 24 gigawatts that the UK wants to generate from nuclear power by 2050. And on here you could see the planned nuclear, like what we already have, the proposed nuclear power reactors. Those were cancelled, so those were projects that were cancelled. So technically this doesn't exist, and so we can't really take them into account. But just wanted to add them to give perspective. And so if we were to fill this gap, the one that we kind of need to figure out from now till 2050, it would cost around 5 to 10 billion pounds. And so it's quite crucial to look at how this would affect the financial, strategic, and policy challenges involved in this, right? We really need to consider how we're going to start financing nuclear power plants. And in terms of required skill sets, again, there's quite a bit of this on this in the paper, but there's quite a few critical skill areas that you need when it comes to constructing like a nuclear power plant. So for example, project and program management, engineering expertise, a safety case, and safety engineers, a lot of research and development. And so one of the things that you see in the paper is that actually, which is highlighted here, there's an aging workforce, and there's quite a bit of a skills gap because we kind of didn't do a lot of nuclear power for somewhat of a generation. And so the aging workforce would mean that we might be missing out on information and skills that we might not be able to pass on to the upcoming generation. And also, one of the things that we kind of need to look at is that there's actually a declining influx of new graduates, especially in nuclear engineering. And that's another thing that we would need to kind of figure out. So it's not just losing the skills and information from older generations that are about to retire, but also the fact that we don't even have enough graduates right now to accommodate what we need to do when it comes to nuclear power. So those two things are things that we need to consider. And so we need to consider things like education and training programs, apprenticeships, just making sure that maybe integrating nuclear-specific skills into universities, just making sure these kind of things are not lost for the upcoming generation, especially that, as I said, we have quite ambitious targets when it comes to nuclear power. And so lastly, I just kind of want to go through briefly some of the policy recommendations that we look into. So diversify funding sources, so essentially looking at financing mechanisms. How can we be financing nuclear power plants in a way that makes it attractive to new investors? Developing education and training initiatives. So I already touched upon this in the previous slide. So just looking at how are we going to maintain the skills and information that we need within the upcoming generations. Promoting international partnerships, looking at how we can, knowledge transfer between countries. And as I said, there's quite a few major players around the world. And so just kind of looking at fostering those collaborations and making sure that we share knowledge and hence reduce the costs and enhance security in reactor design, fuel, supply, and waste management. Engage in public dialogue. One of the things that I haven't touched upon in this presentation, but generally is quite important, is looking into engaging with the public, right? Because a lot of this will be built around someone, somewhere, and so we need to kind of really look at how we can do that, engaging in this public dialogue and being transparent and addressing the public concerns. And emphasizing the benefits, such as the low carbon footprint, the energy security, the economic growth, and innovation potential. And last but not least, but investing in research and innovation. Actually, we had a very nice talk with some of the panelists just before coming here. So investing in things like SMRs might be quite beneficial, maybe not in, I don't know, but maybe not in a whole baseload of the UK, but it would be very beneficial for things like our, again, very ambitious targets when it comes to sustainable aviation fuels or direct air capture or like carbon removal in general. And with that, thank you so much. I think I'll leave it to the panelists, but if you have any questions, please do let me know.
Thank you very much, Adi. So I'd like to ask our panelists to come down to the Great, so I'll just introduce our three panelists, and I will give them an opportunity to spend a few minutes basically explaining their thoughts on the area, and then we will open to discussions and questions. So our first panelist is Nobuo Tanaka. He's the chairman of the steering committee of the Innovation for Kulo Forum, which was established by former Prime Minister Shinzo Abe, Japanese Prime Minister, in 2014. He began his career in 1933 in the Ministry for Economy, Trade and Industry, served in a number of high-ranking positions, and most importantly, he was former executive director of the International Energy Agency between 2007 and 2011. Thank you. So thank you very much to be here. Hisashi Yoshikawa. He's a project professor of the Graduate School of Public Policy in the University of Tokyo, as well as the research director for the Cannon Institute for Global Studies. He's also worked in the International Energy Agency and in the Ministry of Economy, Trade and Industry, METI. And finally, Dr. Mike Bluck here is the director for the Centre for Nuclear Engineering here at Imperial College. He coordinates nuclear research, teaching and outreach, including the provision of advice to government and parliaments. He's also the director of the Rolls-Royce Nuclear University Technology Centre, supporting research for both the nuclear submarine and new SMR programmes. So I'd like to ask Mr. Tanaka to begin with his thoughts.
Okay, thank you very much, Aidan and Nadine, for inviting us to this seminar. Certainly the nuclear power is getting more and more important because of the challenge for the decarbonization. The nuclear is a very important part of the solution. It cannot solve everything, but definitely without nuclear power, it could be very difficult to achieve net zero. Renewables increase very much dramatically and cost is declining. So the challenge for the nuclear is, can it be competitive enough to achieve decarbonization together with prevailing renewable energy source? And Nadine's explanation about the cost is very interesting. Certainly, the capital cost is a decisive factor for the nuclear to be competitive. But the another thing is the risk coming with the nuclear is the issue. Japan has two kinds of trauma of nuclear power. The first one is the Fukushima, the big accident in 2011. And also trauma of Hiroshima, Nagasaki, the bomb is creating the huge anti-nuclear sentiment in Japan. Now I think after this Ukraine war by Russian invasion, it is making more Japanese accepting the nuclear power as a possible energy security, let's say, source. We don't need to import the major, let's say, fossil fuels like gas and oil from Russia. If not, nuclear is much more independent source. So Japanese public, probably 60% of the general public is supporting the nuclear power, especially restarting of them. Most of all of the reactors shut down after the Fukushima accident to check its safety by the very stringent new safety rules introduced by the Japanese, let's say, agency, nuclear safety agency. Now it's about 12 reactors are now running. The Prime Minister said we may restart 17 of them by the end of last year. We didn't go that far, but at least 12 reactors are now running. Can we go gradually? This will increase, but still, reaction to the public is yes, in general supportive, but in the localities, this is a little bit tricky. It's a political issue. The governor is not supporting restarting because he believes that in his region, the majority is still against, even though the general public is in favor. So how to overcome this political issue is certainly the very, very important issue for Japan. To overcome these political issues, I think at Canon Institute of Global Studies, we discuss what kind of sustainability conditions we need in addition to the net zero, decarbonization as well as energy security. We came up with three conditions. The first one is safety or minimizing the risk by smaller reactor, like SMRs, and passive safety technologies. And secondly, to address the issue of radioactive waste is very, very important, including the meltdown debris of Fukushima. Without clear solution to this legacy of the nuclear power, Japanese public is very reluctant. There are three candidates in Japan for the final disposal site, but not yet clearly decided where to go. There's some technology which I pick up in the tonight's session. It is called Integral Fast Reactor of Idaho National Laboratory in the US. Can make the waste the issue of 300 years rather than 300,000 years. 300 years is long, but much better than 300,000 years. So it can be managed by human. So maybe with this technology, we can find a place of disposal much easier. It's not easy, but it could be easier. And so also find a solution for Fukushima debris. So this is the second condition. The third one is the Hiroshima Nagasaki legacy, and how can nuclear technology be proliferation resistant, avoid weaponization. After Ukraine invasion of Russia, if Ukraine maintain one or two nuclear bomb and missiles, Russia may not have invaded Ukraine. So not only North Korea, Iran, Turkey, Saudi Arabia, everybody may want to have a weapon. And it's a disaster. and the nuclear war could be imminent if that happens. So how can we stop the proliferation by some technology, which is the case, which this integral fast reactor may contribute. So I'm arguing that with this kind of technology, maybe public may accept. The cost of large light water reactor, which Nadine explains, is getting higher and higher. Can we continue building with this large light water reactor now? I am a little bit skeptical. Without certain government help, it is necessary, but can we continue if renewables is getting cheaper and cheaper? Is it politically possible to provide? The UK is thinking about a kind of contract for different type of support for nuclear called regulated asset base. Yeah, it's a good try. I think Japanese government is also learning this exercise and try to provide the support, but is it politically viable? This is a very interesting and difficult solution. I think nuclear is necessary for decarbonization, but at the same time, we argue that for the national security, we may need nuclear. Japan is not interested in building weapons after Hiroshima and Nagasaki, but at least maintain the capability is needed. While North Korea is threatening us by shooting the missiles over us from time to time, Russia is definitely there, China is there. Without capability, at least, Japan cannot survive. So the cost of nuclear must be judged the need for national security. So then what kind of reactor can help us to maintain the capability is an interesting question. I am promoting the idea of building the nuclear submarine like UK, Australia, and US, AUKUS. Joining AUKUS is one way, but I'm promoting the idea of having jointly contribute building the nuclear submarine by Korea, Japan, and the United States, Northeast Asian AUKUS. This is a kind of idea to maintaining nuclear capability while adjusting the cost of requirement. So my question to Morin is, this regulated asset base is working here? Or is there a good way of making the cost for nuclear be competitive to the renewable energy is my question.
Thank you very much. Yoshika.
Yes. Okay. Thank you, Aiden, for a very kind introduction. And I have to congratulate the authors of this white paper with successful launch of this white paper. Particularly Nadine, thank you very much for your very thorough explanation of the report. Having heard what Tanaka-san said, I have a small comment on his remarks, and then I'll go on to the comment to Nadine. Firstly, I have a slightly different idea about the mood toward nuclear power generation in Japan. Probably, I don't think that 60% of the people are supporting nuclear. I don't think so. You see, the mood against nuclear is still very solid, I should say. But we don't know. We don't know. But I also feel that recently, the general mood among the people has been changing more for nuclear. That's for sure. But I don't think it is still an important factor when we think about nuclear policy. Mm-hmm. This is the first thing. And the other thing, I just want to respond to what Nadine explained to us. First of all, I was a bit, I'm impressed that in the UK, you have very similar challenges with Japan. We have the issue, of course, as Tanaka-san just said. You see, the scheduling period for the construction is still a big issue. And thirdly, the back end, so nuclear waste management is a big issue we have to consider. But based on the reality in Japan in terms of nuclear, I would say I would add two things. The first one is anti-nuclear mood. That is the first one. Government and the nuclear industry should pay more careful attention on communication, effective communication, or transparent decision-making in terms of future design of the policy and industry structure and all these things. This is the first thing. And the other thing is that given the reality of a very difficult time after Fukushima accident, probably we will need a bit more determined nationwide political will to go for nuclear for the future. If we continue nuclear, if we continue to construct new power reactors in the future, taking the additional factors, national securities, taking all these reality of the East Asian countries into consideration. The issue in Japan, nuclear issue, will go beyond the boundary of energy or economy. If we discuss only in the field of energy policy, economy, or nuclear, I don't think we have a future for nuclear power generation. So that's it from myself. Thank you very much.
Thank you very much. So two contrasting views. And finally, Mike Bluck.
So again, thanks for the report and the presentation. I think it's many very important points. As I see it, there are sort of 4 bits really. Cost is one, closely related, time, as you mentioned, fear, and the skills. And I think you brought that out really well. Cost is clearly influenced by selections. It's an investment problem. Taken as a standard investment problem, nuclear comes with baggage. Okay, and there are a range of approaches to this. You can either take a national endeavour, publicly funded model, where the risk, because the cost is about risk, the discount rate is about risk. It's investor risk. If the government is willing to take on, the taxpayer, the public, take on that risk, okay, then you're in a better situation. If you want to hive it off to the private sector, that's harder. They want a return, and they are risk averse. So I think what we've learned in the UK from Hinkley Point C, the contract for difference, that was an attempt to hive it off. Yeah, and that was a political reason for that. So government has a role to play in choosing this to happen, and that made it was a significant contribution to making it expensive. It's why we're looking at the RAB model now for Sizewell C. They are expensive, but as Nadine pointed out, that LCOE, be very wary about comparing apples and oranges. It's clear that renewables are getting cheaper. What we're seeing is it's the grid costs, the cost of managing the intermittency, that is now the problem. Yeah, if it's the total cost that matters, and that is a problem for renewables now, as much as it is for nuclear. Second of these things, time. Hinkley Point C, initial investment decision to go ahead, 2012, we're looking at 2028 really. This is terrible vote of 14 years in the US. EPRs in other countries have taken an enormous amount of time. So we've convinced ourselves that's how it has to be. France, so we're looking at 24 gigawatts in about 24 years. Let's say it's a gigawatt a year. It sounds absurd on the basis of Hinkley Point C, but there are 400 reactors. Don't look at one. If you were to consider France 1980s, 1990s, they were deploying over 1 gigawatt a year for about 20 years, easily. Japan was as well. Okay. Germany, rather ironically, they've been their nuclear reactors, they built them really fast. It is possible. There are regulatory issues. The finances come back into it. If you have a complex financial environment, it takes a long time to decide how to go forward. But you can do it. The United Arab Emirates has deployed 4 nuclear reactors, South Korean designs, in about 12 years. Okay, now. So it's not. So if anyone says it's not possible now, yes, it is. But regulation is an issue.
Right.
The third point I'd make is fear. So people are terrified of the waste. That's the biggest thing, isn't it?
Yeah, I agree.
Number of people killed by civilian waste. Any idea? 1 million? 1,000? Let's get all the way to 0. And this isn't because the UK has been excellent at managing its waste. It's been criminally incompetent at selling things. Yet they still haven't managed to kill anyone. Yet we are terrified of stuff. And can I say, stuff that remains radioactive for 300,000 years means it's not very radioactive at all.
Right.
Yeah? The stuff that will kill you is cesium-137, strontium-90. That's what you're worried about, gone in 300 years. So even if you don't bother with a fast reactor, an actidine burner, the fear is not where it should be. Actually, let me put it more, focus it even more. Nuclear reactors generate radioactive isotopes that are used in treating cancer.
Sure.
They've saved, even if you factor in the accidents, many times more lives than it's taken. And the final one is skills. You're absolutely right, skills.
Right.
The Nuclear Skills Task Force says we need 100,000 people. We're one of the few institutions which even runs with nuclear engineering degree. Yeah, it's desperate. And I'm in meetings, and by the way, AUKUS, the Australians want 40,000. I was in meetings with them yesterday. Yeah, and they are relying upon us to help them. I'm thinking. So we need to act fast and be ambitious, and not think it's all not possible, because then it won't be possible.
Interesting.
Thank you very much for your excellent contributions. So, I'd like to open the floor for any comments or questions, or any questions really. And there's also, if you're online, please ask questions in the chat box. Great, we've got a question up there. A roving mic.
Thank you very much for your talk. It was very insightful. I would like to ask, Dr. Nadine as well and everyone on the panel, as to why nuclear fusion was not involved in this white paper, because it is about nuclear, and nuclear does include fusion, not just fission. I do realize that most people, I think it was, I forgot, there was another conference on nuclear last year. I think it was at Imperial or somewhere else, and the panel, they all agreed that fusion wasn't a possibility for the next 15 or 20 years. I did my research last year, my internship, on what it would take to meet 1% of the global energy demand with nuclear fusion, and it would take approximately 100 million people for a workforce and $10.8 trillion for costs and everything else. And that does seem impossible, but it could radically change a lot of things in energy. So, and it can address things like waste and everything else. So do you think that taking our focus away from fission and looking into fusion as an alternative, would that be fruitful to solve the current energy crisis we're facing? Thank you very much.
Thank you.
Nadia, would you like to?
Yeah, I can briefly respond to why it wasn't included in the report. I think at some point when you're writing a report, you have to decide what's out of scope. And so this report was already like more than 80 pages. And so we wanted to focus on nuclear fission. That's not to say that nuclear fission doesn't have a role, and it's more that we wanted to focus on what we need to do right now to reach our 24 gigawatts of electricity from nuclear power. And so I think in this paper, we kind of wanted to focus on that. Like, what are the recommendations that we need to do within the next, 5 years, if not tomorrow, right? Yeah. Whereas there's a lot of different things that we need to reach net zero. I think I'm the first one to say that there is no silver bullet when it comes to reaching net zero globally, because you have to consider the fact that there are different resources depending on the country you're looking at, different national sovereignties, like as we can see between Japan and the UK. And so, yeah, there's no silver bullet. But for the case of this paper, we focused on nuclear fission for the reasons I mentioned. That's not to say that nuclear fusion won't have a role. It's more that we wanted things to look at immediate right now.
Yeah, I mean, that's very correct. It's just basically...
Yeah, I think fusion is a very good... I hope it is a great chance. And fusion's kind of international collaboration is called ITER, in building the huge fusion reactor in Cadarache in France. Japan is contributing, UK is contributing. It's a global joint venture.
Right.
Though, as an international, and it's a big thing, and it's a standard. But now there are many small commercial fusion companies rising in these couple of years. Yeah. And certainly some of them claim they will generate electricity by 2028 even, or early 2030s. Microsoft invest one of them for their own in-house electricity. Who knows which one will succeed? I'm not an engineer background, so I don't know which one succeeds. But if one succeeds, just as you say, it's a revolution.
Right.
So I still keep the hope there, but I'm not sure if any of them succeed by the end of 2020 or early 2030.
Any other comments on this?
Yeah, if I could, I am an engineer, and I work in fusion as well as fission. Okay.
Very good.
Yeah, no, it's great fun. ITER is not going well, and there's been a shift to smaller designs, spherical tokamaks. There's one example. One thing to say from the engineering side, making fusion happen is ludicrously easy. Anyone in this room could buy the components necessary and do it in the shed in their back garden if you have them. Making fusion happen between deuterium and tritium is really quite straightforward. Making it happen often enough and sustaining it, that is so hard. It's horrific. And so the big principal challenge is material. The generation of all of these reactions, most of them generate hugely powerful neutrons which decimate materials. That's the main challenge. And we don't have those materials yet. And we don't know when we will get them. That's the uncertainty. So by 2028, I mean, well done. If you're a billionaire and you haven't invested in a fusion venture, then you probably don't get invited to the right parties. It's somewhere but remember, I work in fusion. I like it. It's great. Scientifically, really interesting. But the challenges are enormous. And between you and me, I know some very well-connected people. That sounds like a threat. No, I do. Some very well-connected, very, and they don't see it making any contribution this side of 2050. Okay, so, and I should say, the UK, up until very recently, you talk about investments, we should invest. Government investment in fission was 1/10 of its investment in fusion over the last 30 years. So it's not like money isn't being thrown into it. Actually, fission is the poor person when it comes to looking at these things. But I I hope it works because it's fascinating.
Yeah, interesting. Let me add one
Yeah.
small remark. I'm inspired by your remarks. I have to confess that I started to work in the government 1981, working on nuclear policy at that time. And you see, I was really amazed to see the budget on the fusion were already there in Japan. So 1981 is, well, half century ago? No, 40 years ago, something like that. So we have been paying, you see, effort on developing fusion for the last couple of decades already. So I hope, I couldn't agree more on Tanaka-san's remark, but I hope it will become real in the near future. But we have to be very realistic. That's how I see it, just for your information.
Brilliant, thank you. Any other questions? So there's one there in the middle.
Thank you so much for the presentation and the talk. My question is on regulation. Is there specific regulation or policies that are really seen as obstacles and sort of need sorting out in the UK or in other countries as well?
I think this is a good question. So you, Mike.
Okay. Regulation has come up. Clearly we're taking age to build. Hinkley Point C, and there's a concern. Regulation and how we potentially adapt it, notably for SMR, in the future is a big question. There was a hackathon actually in April, run by the government to sort of brainstorm approaches to regulation. Nuclear has a unique regulatory position in that we have to license, each jurisdiction has to license its own thing. Yeah, so the fact that the EPR was being built elsewhere, it was a French-German design and was being built in France and in Finland, meant nothing. Our regulator sits there and says, go ahead, prove it safe, all over again. 7,000 changes to that EPR required by the regulator. If we did it for the aircraft business would go out. If everywhere any aircraft landed, there was a full indigenous regulatory process, no one would be flying anywhere. We wouldn't have aircraft. Same for many other industries. So, and this has been recognised. So I think there is a need to possibly accept some sort of intergovernmental acceptance of regulation, I think would help. But more than that, I think if you look at our regulatory experience, say Sizewell B. Sizewell B got the go-ahead in 1982, started building 1987. And then was on the grid 1995, and it was at cost and on target. 5 years for a public inquiry. Yeah, if we're going to have a 5-year public inquiry, and if you look at EPR, it was no different really, for every single reactor that we implement, then we are going to have a problem. So I do think this needs some triaging. There are some it's really important that we ensure that we have a strong regulatory protocol, but also we need to be able to say, look, I'm sorry, but this isn't really serious. Yeah, I mean, somebody has got to make a decision as whether whether the effect on a local bird sanctuary is really relevant to providing us with 10% of low carbon electricity. Somebody's going to have to make a decision a bit quicker than 5 years.
Yeah, UK is probably the country where you are testing more, enabling regulations. We need a reform of a regulation. Otherwise, small modular reactors, Michael mentioned, it's very difficult.
Right.
So, together with regulators and vendors or utilities, I think they have to think about the new framework for regulation. Otherwise, transaction cost of small modular reactor, because one reactor is accepted, then anywhere it can be built without one by one licensing. Otherwise, SMR will not work. So definitely, international collaboration and harmonized way of new regulatory framework is necessary to make nuclear as a much more, a prevailing, successful mode
Realistic,
of energy. Yeah.
Agree.
Brilliant. We've got a question online, do we, Louise?
Someone's asked, the portion of nuclear fuel costs in the 6 scenarios are quite small, and are they all based on the current nuclear fuel market prices? So I guess that's one for Nadine.
It's a question for Nadine, yeah.
Yes, they're all based on current prices with references, so you'll find that in the paper.
Short and sweet. Any questions? Any other questions? Got time for a couple more. Yes.
Thank you. This is about SMRs, and you've mentioned it quite a lot in your answers, and it also came up in the presentation, I think. Are we at risk of putting too much faith in SMRs, much like nuclear fusion? Because it appears to, it comes up in so many different plans, and is that something that's actually going to happen? Thank you.
Good question. I mean, the nuclear small modular reactor has been developed and discussed 2 decades or more
Already.
but it never be built except Russia and China. So will it be built somewhere? It depends on the user, or it depends on the demand. I am now watching carefully what megatech firms will do because of the need of decarbonized electricity for data centers or use of AI. This sector will need very stable supply green electricity. The SMR could be the choice. Microsoft is investing in small modular reactor for their own use, and even fusion. And the Dow Chemical is trying to use the small reactor of high temperature gas reactor, X energy, in their plant in Texas or Louisiana. So this kind of industrial use of SMR makes it very different. I hope this will happen sooner or later, because already 20 years we lost.
Yeah.
But this very big change of climate crisis, as well as electricity crisis of AI and data center, may make a difference for SMR.
Sure. Well, I couldn't agree more with what Tanaka-san just said. But let me add 2 things. One, demand side consideration is really important, as he said. But at the same time, is with SMR, the siting could be easier? I don't know. In Japan, based on the reality in Japan, I don't think so. So we have to consider this. But at the same time, concerning cost, what Nadine presented before, you see, the cost of SMR will not be that small. So we have to examine the cost carefully, probably. But there are many, many preconditions which will affect the cost in the future.
Your assessment is AP1000 and SMR is almost equal.
Yeah, so SMRs actually, I know they're marketed right now as the reactors that will have lower cost because they're smaller, but obviously that's not the case right now because we haven't commercialized it yet, right? So the cost of any technology goes lower as you start commercializing it. Yeah. And so right now, no, you don't see that in the economic analysis. It is expensive. I mean, you could go further and start looking into learning rates and how that would drive the cost down, but that wasn't done for this case. Sure. Just because of the near term. As I said, the focus of this paper was very near term, what we need to do now, especially that a lot of the things we mentioned we already know how to do, right? And we're still failing at that. So in hindsight, like, the other things that we don't know how to do yet.
Interesting.
Yeah, I'd agree with you to the extent there's been a bit of a market rush to go SMR, isn't it? The silver bullet that fixes everything. When actually we can build big reactors as well, as we've seen the world can, okay? But I wouldn't lump SMR into the same bin as fusion, yeah? SMR, it's just a smaller version. Mm-hmm. They weren't always this big. The very first reactors we built were small, yeah? It's just economics drove them, the economic model drove them to be big. So we can build small reactors. For example, the Rolls-Royce SMR, Rolls-Royce build quite a few small reactors and have done for many years. They sit in the backs of submarines. Yeah, these are really small. But that is not the technology, by the way, that Rolls-Royce SMR are proposing. Rolls-Royce SMR have gone for, let's bore the market into submission. This is such an ordinary design. It is like Sizewell B, but shrunk a bit. Yeah? I mean, there are some technical differences in terms of, the boron shim and so on. But their whole idea is this is conventional technology. It's barely, it's Gen 3, it's not Gen 4. The idea is the cost savings come from making lots of them, and it's production technology and learning that will bring the cost down. Okay, but equally, some SMRs are out there. They're Gen 4 technology, and they're way off. Yeah, I agree. But I think there is a market for them, as you've mentioned a few.
Interesting.
Brilliant, thank you. We've only got about a minute left. Has anyone got a quick question to ask?
This is a follow-on question on SMRs. There seems to be a tension between the huge gap that we need to fill and the focus on small modular reactors. Should more attention be on ways to make large gigawatt reactors more efficient, modularized?
Yes, but in a sense, modularized, they are big. There's a bit of a misnomer. There's lots of versions of modular. Some of them are build the entire reactor in the thing and ship it out to site. The Rolls SMR is one of those. You're still sending bits out to site. It's just modularity in terms of standardization of valves. And there's various different sort of things. And you can do the same thing with a large reactor. And you should do the same thing with a large reactor. But if you, like an EPR, decide to have a bespoke valve, there are thousands of valves in one of these, for every single bit, there's no standardization, then you are going to pay a price and it will be more expensive. But I agree. I think there is a lot of scope for standardization, that sense of modularity that would come.
Just interested if you have any experience of, I think it was in Vogel where modularization caused a lot of problems.
Yeah.
Has that changed?
So Vogel, I think most of the problems were almost contractual, but you're right. I think there were issues with that. I think there's learning of the learning, if you like. So I think there's a push to get Georgia to build more AP1000s, and of course they're pointing and saying, but they were really expensive and took ages. It's that question, if you've done it once and you now know what the problems are, is this the time to bail out? It's the gambler's sort of difficulty, but I think there's a lot that can be done in regulation and in the manufacturing of nuclear of any size that can lead to considerable cost savings. Build more, just build more of everything. Once you've got a design that works, just keep building it. That's a lesson that tends to be.
It's a good lesson. Interesting. It's a good lesson to end on,
That's the French way.
Yeah, that's the French way. That's the French did it.
Yeah, they did build a similar reactor or same reactor for 40, 50. And that's the reason why they keep the cost low. The US took the totally opposite way. Boiling water reactor, pressurized water reactor, different companies, they are using the different colors for cables. How could you keep safe and cheap in this kind of setting?
Probably Japan as well.
Yeah, exactly. Japan made a mistake. Korea good job.
job.
China did good job for maintaining cost low
Right.
because of standardization and modularization. It's without question.
Can I add just one thing? Those challenges are actually not, only unique to nuclear power. This exists in everything else. So technically, I know I'm here for nuclear power, but technically I'm more of an expert in carbon capture and carbon dioxide removal technologies. It's the exact same challenges when it comes to commercialization and learning rates and just, going ahead and doing it and seeing, because in terms of technology, we know it, right? We know it works, we know how to do it. But getting the cost down and just learning more about it means we just need to, go ahead and implement it and see how it works out. So yeah, it's not unique to nuclear power. I would say it's probably everywhere else. Same with sustainable aviation fuels, which Michael and I worked on for a bit. It's the same thing for everything.
Brilliant. Well, thank you very much for all our panelists. So thank you for coming. You will have a link to the full reports sent to your email, and enjoy. Thank you.
Thank you.
Enjoy that.